Good evening. This is Group 9, and we are going to be reviewing the document called Addressing the Straggler Problem for Iterative Convergent Parallel Machine Learning Algorithms. The article was written by the following authors. The exact title is Addressing the Straggler Problem for Iterative Convergent Parallel ML. It is written by Carnegie Mellon University professors in contribution with different students for the research. So the motivation behind this article is to explain current issues with iterative machine learning systems, especially distributed systems. Essentially, data is split into chunks, and those chunks are processed by different systems. So each node, each worker, gets a subset of the problem, at which point they iterate through their calculations and they converge. As they converge, the nodes must synchronize at certain points during the process. So imagine an iteration. Every iteration, all the nodes must converge. They must synchronize their data. And those computational synchronization points are called computational barriers. So the system is only as fast as the slowest running process, because if, let's say, 9 out of 10 nodes finish, but the 10th node is running on a system that is excessively slow, then the process is actually going to run as slow as the slowest node. And that is a problem because time is wasted waiting for that one slow node. And this is the motivation behind the article, where the authors try to address that problem, compare their solution to various other current solutions, and try to prove that their solution is superior to the current solutions. So the question is this an important problem? And the answer is absolutely yes. As mentioned earlier, the entire process only runs as fast as the slowest node. So this leaves a lot of resources wasted on slow systems. Even in high-performance infrastructures, performance slowdowns called jitters, it can have significant impact on the duration of the computation. And as discussed, these jitters occur for various reasons. The big reasons is because current distributed algorithms run in infrastructures that are shared. These infrastructures are shared among different users, and each user has a virtual machine running on the same physical box. And so if user A has excessively complex tasks running on the same physical system, and user B starts complex tasks, that box, the physical machine, is going to get slowed down significantly, which is in turn going to slow down the entire process of the computation. So it's very difficult to solve this problem because it's hard to predict when it could occur, because we actually have no control where our jobs are going to get scheduled on infrastructures like AWS or Azure or other online platforms. Performance jitters is a very important concept by itself. It has various articles discussed, but the main idea is that since our environments are shared, we have no control of the operating systems, the machines, the hardware, and so jitters occur because of random spikes in resource utilization. That in turn creates stragglers. There's often a lot of unpredictable background processes that are executed. It could be maintenance tasks, it could be various other unscheduled or even scheduled processes that the end users are not aware of. So one good question is, are there any solutions out there for this problem? And the answer is yes. There are quite a few attempts at a solution by different applications, frameworks, and different vendors and different architectures. This is not a very long list. This is the list of the approaches that are used in the article. The authors compare their solution to these solutions, and these are in fact one of the more popular solutions for large-scale products that are used by big companies and academics, etc. So the first is BSP, bulk synchronous parallel. This is one of the more popular and I think one of the oldest approaches. And their attempt to solve the straggler problem is not assigning work to stragglers. So they have this blacklisting feature where if they detect a straggler, the system no longer assigns work to those slowing down systems and only assigns work to the ones that are running relatively fast. Another approach is redundant processes in multiple systems. What this means is that as the system is running a computation, duplicated nodes are created with the same exact problem set. So two nodes are essentially racing to completion. So in case a node slows down, the data on the other node gets completed, the processing gets completed faster, and those results are kept, and then the system that is slower, those results are discarded. This is, however, very wasteful, as you need to create more instances and more resources. The second attempt is a variation on BSP. So it's BSP-RR. RR means rapid reassignment. And what this does is it has all of the features of BSP, but it also implements the concept of reassigning work to other nodes. BSP's shortcomings are its strict synchronization barriers. As mentioned before, all of the nodes must complete processing before all the next iteration can begin. So that limitation is still part of this solution. However, the rapid reassignment lets slow nodes offload some of their work to the faster nodes in order to speed up the process. The next famous or popular attempt is SSP, state asynchronous parallel. Now, this attempts to loosen the strict process synchronization barriers that BSP has. So systems no longer have to wait to a very specific point and finish at the same time before they're able to start in the next iteration. What SSP does is it creates a slack number of iterations, which means that any nodes that, let's say, finish iteration 1 are able to go to iteration 2, even though other nodes working on the same piece of the problem are still behind. Now, the iteration slack limit is how many iterations the fastest node could get ahead of the slowest node. So if it's 3, the node can only do 3 iterations ahead of the slowest node, at which point it still has to wait for the slowest node to finish. So this is the slack limit. Another fairly new approach to this problem is a MapReduce architecture. MapReduce is a product by Google. It is what they use to process large quantities of data. And there are many products that implement the MapReduce architecture, like Hadoop. It's one of the very famous open source products. And they use a concept called speculative execution and test cloning. What this does is it's similar to BSP, where tasks are cloned into multiple systems. And the first system to finish its processing is the one that merges its results with the next step and the next step. And all of the redundant tasks are thrown out. So any systems that are stragglers, they're just kind of discarded. This, however, is once again very heavy on resources, so not always the good solution. Another benefit of MapReduce is that tasks are independent and stateless. So what this means is that systems performing calculations do not have to synchronize. Now, there are cases where they have to synchronize, but in many cases, because of its isolated nature, the mappers and the reducers can continue working through some parts of the problem. Eventually, the data has to be brought together and synchronized. However, there's no strict barriers like BSP. So that's a good solution. However, chances are the problem set has to be adjusted to run against this architecture and support the stateless and isolated processing of data. And the last solution that is used in this article is specialized solutions, and these are custom hardware and software designed to mitigate this jitter problem. However, this is we were a little skeptical against the solution because it's very customized. It's not really available to general public. This is not something that is easily acquired. You cannot go to Google or Amazon or Microsoft or any of those infrastructure platforms and get the service of this type. And if you can, there are likely vendors that support this, but the price would probably be too high to be of any actual use. So even though this is mentioned, this is not likely a good solution that is commercially available because it's just too expensive. So this is a more concise list of the current solution limitations as presented in this article. Of course, we have to keep in mind that these are the solutions proposed, or the limitations proposed by the authors who are trying to defend the product, and they include, for BSP, strict synchronization barriers. As we mentioned, it's the requirement that each task has to finish before the next iteration could continue. The blacklisting is fragile. Short-term random slowdowns in fast nodes would cause the node to be blacklisted, essentially eliminating the number of nodes that are able to process the remainder of the problem. BSPRR, it's BSP with rapid reassignment. same limitations as BSP, and the rapid reassignment feature in BSP is not as effective at reassigning work during an iteration as the author's proposed solution, which we'll see shortly. SSP, significant slowdowns could still occur and kind of essentially cause asynchronization barriers because the fast nodes would get to the limit, the slack count limit, and still would have to wait for the slower systems. So essentially you have like a slinky effect where slow systems slow down, that's faster nodes speed up, they wait for the slower nodes to catch up, and then they speed up, and so on. Okay, so a good question is, did the authors motivate convincingly this problem? And the answer is yes. We are actually motivated after reading this article. The authors provided a lot of valid arguments. They clearly explained the problems, both conceptual and technical and theoretical problems, and provided solutions, as we'll see in later slides, to the problem and how their solution addresses these problems and how it compares to current solutions and what's the same and what's different. And that's very important. We judge an article based on its evidence and based on comparisons of their solution to the current solutions without any bias. So they had different environments, they had different problem sets, which we'll see shortly, and they proved, at least according to their numbers, that their solution is a viable solution. We're going to look at the design and the main idea behind the author's proposed solution. Now, FlexRR is the name given to the solution, and it translates into flexible synchronization barriers with rapid reassignment. And the general overview of their design includes flexible synchronization barriers, as we've talked about, rapid reassignment, peer-to-peer communication, work shedding as opposed to work sharing and other approaches, helper groups of various sizes, initial work assignment and follow-up work assignment, and the waterfall shedding pattern, which is, as we'll learn, is an iterative pattern on sharing the work as the node gets more and more congested. We'll start off with looking over the flexible synchronization barriers design, or the part of this solution. And what the authors did is they adopted a variation of the SSP synchronization model, where nodes are allowed to process past an iteration barrier. This, of course, mitigates the limitations of BSP, with potential downtimes. Nodes, as we mentioned, do not have to sit idle while slower nodes finish their iterations. And nodes can potentially have a significant gap between the fastest and the slowest nodes. Now, this problem is, as we'll see next, in the next couple of slides, is mitigated by their rapid reassignment feature. So they actually combined existing features and some novel ideas together to provide a unique load balancing capability of their solution. Peer-to-peer communication is another feature of FlexRR that is a fairly novel approach based on this article. We did not do extensive research on all possible, or not all possible, but other solutions out there to see if they implement a solution similar to this. And so based on this article, their approach uses peer-to-peer communication, which uses a non-blocking message passing interface. Now, this is an interface, it's essentially an industry standard interface for message passing and publish and subscribe paradigms, which essentially creates a channel for a group, and individuals or systems are able to put messages into that channel, and then all the subscribers to this channel would either get push notifications or they would have to pull for notifications, almost like going to your mailbox. Now, in our case, FlexRR nodes pull their mailboxes, their message boxes, for messages from other nodes within their group, and we'll discuss the group in the next couple of slides because it's also part of their design decision to introduce the grouping concept. So you're able to set the polling frequency for each node. In this case, the default is 100, and this is what was tested. Later on, we'll look at the testing and all the problems and test conditions and environments. So the default is 100 checks per iteration. Each node keeps a runtime timer to keep track of how long it has been running. Now, this timer is important because, as we'll see later, it is what peers use as essentially a benchmark, context, point of reference to see if they are actually stragglers in their group. And it's a very simple messaging interface. They have, I mean, there are more, but these are the core messages that are used, which is do this, begun helping, update param, progress report, cancel help, which we'll talk more about these individual messages as we continue with the presentation. Rapid reassignment, as mentioned before, is not a new concept. However, it's used in conjunction with other features of this architecture, this proposed solution. And it essentially, it rebalances processing between node. Now, these nodes are part of a group, which is another, feature of this approach. So these nodes share progress reports within their peers. Slow nodes are able to shed their work to faster nodes within their group, and frequent progress updates allow the system to adjust to stragglers and rebalance the work. Now, this is in conjunction with SSPs, well, similar to SSPs, loose synchronization barriers, because loose barriers allow the system slack in the hopes of the slower nodes eventually catching up to the faster nodes. So rapid reassignment, it goes outside of that boundary and says, okay, if I got past a certain point of lag or slack, to start reassigning the work. So instead of just stopping at the barrier and waiting, eventually once the gap gets too large, you start reassigning work whenever that gap gets to a certain point. And this is an important difference to note, and our authors rely heavily on this reassignment in conjunction with peer-to-peer messaging and groups, as we'll see in a second. So now we talk about the work shedding feature. Now, there are different concepts in terms of work sharing, work shedding. Work sharing is when nodes can reassign work back and forth, and nodes can ask for work from other nodes based on their progress. FlexRR actually uses work shedding. In this case, the nodes that receive progress reports in the group, they check for the values, and they, as I mentioned, compare their work or their progress in this task to their peers and issue do this messages if they're slower. Do this message contains the iteration number, data block, start block, and additional do this messages double in size as they see themselves to still be slow. This is an important concept because nodes detect themselves to be slow and they reassign their own work versus polling other nodes for work. Now, this is arguably a faster process because a node will know that it's slow and choose to share work with its peers versus essentially pinging each peer with asking to do the job. It's less overhead, less processing, less communications. Also, nodes that have requested help from a peer node are able to cancel the request. Now, this is important because if one node is being slow and one node is being fast, the slow node issues a do this command and ask for assistance. Now, if something happens and the slow node all of a sudden becomes much faster, it finishes its task and it can move on to the task that it tried to reassign, it is able to cancel the request and choose to process the data by itself. This is important because as long as the faster nodes, the nodes that was assigned the initial work request, has not acknowledged that it has started, the helper node can tell it to essentially cancel the request. Say, ignore, I just asked you to do this, I will do it myself, which is a very interesting concept as it allows nodes to rebalance and kind of rebalance by themselves without flooding one node and then saying, you know what, now all of a sudden it's faster, but now the fast node becomes slower because a lot of work was reassigned to it. So this is a very interesting concept and a fairly good novel idea when it comes to distributed processing. And now we're going to talk about helper groups. This is a fairly novel idea. Now, the idea by itself is not unique, but the application of it in this context is actually, in our opinion, was fairly unique. So the helper groups essentially are small groups of nodes within a large context of the application that are able to communicate and help each other. Now, this is a unique approach because isolating nodes to smaller subgroups is very performant in terms of network overhead. instead of every node in, let's say, a 100 node cluster communicating with each other to share work and compare progress reports, and flooding the network essentially with 100 by 100, progress reports in the worst case, these are smaller groups. So let's say, for example, a group of 4 nodes that are in the helper group will only send progress reports and assign work to each other within this group, significantly eliminating traffic. Because chances are, if all nodes are processing at the same time, there will be no work assignments. So there's no reason to really flood the entire network with progress reports. As discussed, they do progress reports. The slower nodes will assign messages or assign work using the do this messages on a frequency set during initialization. The timestamps are compared, the work can be canceled, etc. All of this is done is in a small group. And of course, once work is completed, the helper node issues a work complete message on completion. Initial and follow-up work assignments is also not a new idea, but also applied in a very novel way. Slower nodes check for begun helping messages during every message check. If a slower node receives a begun helping message, which signifies that the node it's asking help from has begun processing, and it checks if it's still behind and sends an additional do this message that will issue additional work to the helper node. However, this follow-up work assignment is not the same amount of work. It actually doubles every time. So every time a slow node assigns work, it doubles every time. So this is a very unique approach. However, the authors do not really go into a lot of detail regarding the extreme cases of this. It was our assumption that this could actually potentially backfire if the requests get too large, and in which case the work assignment would be so large that then the helper node would essentially become the straggler of the process, and then start asking additional help from its peers, passing work back and forth. The processing would essentially get very lopsided, and you would rely on a lot of work passing back and forth. So this is a novel idea, but we could not find a lot of backing evidence that says that this is, in the extreme case, would work. So as always, most of this configuration could be set during initialization. So you don't have to set it to be double the work, but this is what the authors use to kind of represent how this is a novel idea and how this works. So we would have to trust them at their word. This leads us into the follow-up to the the overloaded node with the waterfall shedding pattern that the system implements. So what this does is that it tries to rebalance the nodes essentially iteratively. So any node that becomes the bottleneck is essentially going to restart the process of rebalancing. So if node A was the straggler, assigns its work to node B. Node B then becomes a straggler. It reassigns its work to its peers based on the same process, progress reports, do this, etc. So once again, this has us concerned about the extreme cases and what would be involved if the work reassignment essentially starts eating up a lot of network bandwidth, where nodes keep getting hammered with requests and they keep slowing down and reassigning work. Once again, authors don't really go into this in great detail. But like mentioned earlier, there are various settings that could be adjusted to prevent this type of situation. It's just our personal skepticism. And what's interesting about this waterfall pattern is that the node in the helper group, the helper of the original node, might not even be the node that executes the assignment, the work assignment. Because if node A assigns to node B and node B slowed down, it could assign the work to node C, and node C, if it slowed down, node D, etc. So the node, the distant cousin of the group, can essentially do the work, which is a different pattern that we've seen so far with other approaches, where usually the same node or a very cloned node is executing the work. This means that a distant cousin of the group could execute the work in parallel, which is a novel idea for sure. Now we're going to look over a short list of similarities to current solutions. So loosening the process synchronization barriers, very similar to SSP. slack iteration, which is essentially what FlexRR does, in addition to its other features to kind of support it. Parameter server for storing state information between iterations. This seems to be a common pattern where between every iteration, the state of the application is stored, data is kind of merged. A lot of systems do this. Work shedding is actually similar to or BSP blacklist feature. Maybe not a direct comparison, but essentially slower nodes are not assigned work, and the faster nodes get assigned work. Rapid reassignment is also similar to BSPs. It's a very basic rapid reassignment. It just doesn't have the loose synchronization barriers that FlexRR has. The difference is where we believe FlexRR has one of the most interesting features. And peer-to-peer communication for work shedding and reassignment. That's a very unique feature, even though we didn't see this in the document. Some research online also showed that this is not a very common approach, and it was combined in a novel fashion. Peer-to-peer communication does exist, but the whole grouping mechanism combined with rapid reassignment, the iterative rapid reassignment, so the waterfall model, all of these are a very unique combination, even though they're very well-known solutions that have been used in the past. But FlexRR does a very good job combining these solutions to provide a very robust and an interesting architecture for a problem that actually does seem to work very well. Now we're going to try to talk about the implementation details. These are some of the more a brief overview of some of the lower level details of FlexRR implementation, its core designs. Parallel execution and control. So essentially, there's one process in each node. Processes start a worker thread for each CPU core on the node. Now, this could be a single machine, or it could be multiple machines on the network. There are background threads started for each internal node's functionality. So kind of like the administrative work for the actual application, management of resources, etc. And the flexible synchronization barriers. So these are the mechanisms that calculate the kind of the slack that the system has. And there's a set of processes that maintain the parameter server, which they extract values for these iterations, and they make sure these values are synchronized with the parameter server. So each machine does this to make sure the process is healthy and kept up to date. The worker execution management involves the list of cores or nodes, if you're using multiple systems, that are going to be used during the initialization. So that when the process starts, you supply the resources that the system will get, both in terms of physical machines and the processors and cores on those physical machines. And the system, based on its internal logic, kind of sets itself up to use the resources that it's allocated. Each worker thread is issued an ID from 1 to n, which is the number of nodes in the cluster that's going to be doing the computation. So if we have 100, each one is going to have an ID from 1 to 100, and as well as input data for each node. So essentially the nodes are tagged, so they're identifiable, they're unique, and their data is fed into the node for processing, as well as the stopping criteria. So for various different problems that distributed systems attempt to solve, they have very specific end criteria which the system must know how to end. So this process is fed the end criteria, the data, the function code that actually processes each item, because essentially these frameworks are just frameworks. They actually don't have any internal logic on how to solve your particular problem. They implement the communication mechanisms, the management, the work assignment, the balancing, but the developer's job is to implement the actual processing, the logic behind the processing. So these are the data that you feed into the system. Parameter server for shared data. It involves essentially storing data from each iteration. So once the iteration is finished, data is centralized stored in a centralized server and fed into the next iteration. It implements a very simple command API. API stands for Application Programming Interface. It is the commands that the server knows how to respond to, and it implements a read param and an update param commands. Read param, I mean, the name is descriptive. It essentially reads a specific piece of data specified by the metadata sent with the request, and an update param. It's important to note that updates to the system must be associative or commutative. This means that the order of commands should not matter on the result. Like, for example, addition. 2 plus 2, is the same. 2 plus 3, 3 plus 2 will also get you the same answers. This is very important because there's no way to control the completion times in a distributed system. Race conditions happen all the time. Certain nodes will finish at random orders. So if the system was not commutative or associative, it would be very unpredictable and would be very difficult to solve, as well as it would probably institute extremely strict synchronization barriers. So those are very important things to note. And also straggler mitigation. As we talked about, it implements peer-to-peer communications and work reassignment, as well as loose synchronization barriers to combat stragglers. We've seen straggler identification. What's important to note about this slide is the do this work reassignment call. It's interesting because nodes are actually able to assign parts of a process, a batch of work, starting at a particular point and ending at a particular point. Now, again, authors didn't go into detail about this. Our assumption was that the data must be set up very specifically to accommodate this work reassignment pattern. Because if you're unable to break up a job in the middle of a process, essentially, continuity, if you break the process in two, then the data processing may not make any sense out of context of that, that iteration. So that implementation detail, even though it's discussed, it is not elaborated. So that's also, we're a little bit skeptical about how that may work. Other than that, the follow-up work fairly straightforward, doubling every time, dependent on the configuration settings. Work reassignment cancellation follows the same basic peer-to-peer communication pattern, where if the node that has issued a command or issued a do this command has not received a confirmation by the time it has recovered its processing, I guess, timeline, or recovered, got to a certain point in time where it's able to process more work, it's able to cancel the request that it's made to its helper. So that's actually very important. So you're not actually creating stragglers by being one, by assigning too much work to another node. Now we're going to look at the evaluation of their algorithm, of their architecture. The authors actually did demonstrate fairly well that their solution works. They compared their results against the current implementations for similar problems. They actually had significant material in their article describing their different setups, their different environments, different contexts, different problems. They provided various test scenarios on different systems, infrastructures, and configurations, which is actually very impressive, and it proves that they tried to present the best possible evidence. They also presented different environments with different degree of computational resources, which is also important because if you demonstrate your algorithm on an extremely fast and expensive system and it works well, it doesn't mean it's going to work well on something very inexpensive and low powered. They applied the solution to a lot of dissimilar tasks with unique computational models. So that also proves that their approach doesn't only fit a niche market of problems. And that's also very important because if you're going to propose a solution to a large issue, it makes it more convincing that it's able to be applied to multiple different problems. They also compared the results and provided results using different configuration settings. So that's also a lot of information to look over and to kind of make conclusions about whether their algorithm works or not. And we really appreciated all that effort. They also, they used various standard popular platforms like Amazon EC2, Microsoft Azure, as well as more custom settings or custom environments. different sizes of VMs, node counts, etc. The test scenarios they provided involved slow worker pattern, disrupted machine pattern, and power law pattern. Slow worker pattern, it artificially injects tasks to certain nodes to slow them down on purpose and see how the system reacts. So they tested the various settings, various percentages of it during an iteration where a node, let's say, would slow down by a factor of half, or slow it down by 10%, etc. Now, disrupted machine pattern is similar. It significantly would slow down processing in the machine. It would cripple nodes to the point where they couldn't do any work. It was also a very good test for their algorithm, in our opinion. And the power law pattern, which that is what we were very curious to see, the results for that. The power law pattern it essentially puts a lopsided amount of processing into the system, and it sees how the system rebalances itself, which we believe is a very, very good problem to throw at something like this, since they claim rapid reassignment with peer-to-peer communication is going to provide the best possible results. And it actually did show that their algorithm outperforms almost every other one that they compared to. Once again, this is them comparing their results to these algorithms. We did not do excessive research to find other algorithms that are addressing these type of problems. The problem sets were matrix factorization, multinomial logistic regression, and latent Dirichlet allocation. These are typical problems that are not unique to any particular field. These are problems that are being solved all the time. So it was very interesting to see that they chose these problems, and we appreciated that the algorithm actually handled these problems fairly well. This chart shows the execution of their algorithm and the particular problem set. So this chart shows EC2 instance running the LDA with no injected delays. So this was literally to just run the system through its input set and see the outputs and how long it's going to take. And on this side, it is executing matrix factorization with no injected delays on a large cluster of custom hardware. So as you can see, FlexRR is in pink, and it outperformed every other algorithm that was previously used in the industry. In this chart, you can see the same matrix factorization with no injected delays performed on Microsoft Azure on both A4 and A3 standard machines. And in every case, FlexRR significantly outperformed its competitors. In conclusion, we just wanted to answer a few questions. Did the authors achieve what they set out to do? We believe so. The authors clearly explained their proposed solution. They clearly explained their problem. They provided significant evidence for their solution. They compare their solutions to current industry standards, which is very important because you want to know how your solution compares to essentially the giants of the industry. And they included evidence and benchmarks proving their claims, and that's also very important to go to the lengths of renting various servers, running through various combinations of problems and synthetic benchmarks and actual benchmarks. It's very involved, and in the end, to show that your algorithm works is a very admirable effort. And I believe that the authors achieved what they were trying to prove. Was the paper well organized? Yes, the paper was extremely well organized. It was, it opened up with an introduction to the problem. It explained what the current solutions are, explained some of the benefits of the current solutions, how they attempt to approach, problems, and then they were very clearly laid out their solution, the solution high-level overview, and the low-level implementation, which was it was good to see that this was not just a theoretical article or what may happen or could happen, but it actually is a very technically well-written article. We learned a great deal from this paper. We actually, coming into this, did not know much about BSP, SSP, various synchronization mechanisms, various frameworks for job scheduling, for load balancing, and this is a very informative paper that introduced a lot of new material and a lot of interesting new material. So, it lets us appreciate. It made us appreciate the complexities of cloud computing and distributed systems and all of the massive amounts of data and the complex computational problems that exist that are being actively worked on, and how all these clever approaches iterate over current solutions and provide better and better performance. And that was very, very interesting to read. And lastly, we want to mention how this is a very practical and important idea. We really appreciated the fact that this article does provide a technical solution to a problem, not something theoretical or something that could happen if our computing power doubled every 10 years or so. But this was a very well designed, thought out, and tested practical approach to a current problem that seems to outperform, at least according to the authors, current solutions. Once again, we reiterate that we did not do extensive research into the field, but from the research we did do, we did find that the solution compared very well to current industry standards, and the comparisons made in this article are legitimate and clear. And is this an original idea? It is incremental, absolutely. The idea is not necessary. Credit should be given to the authors, absolutely, but the idea itself is not necessarily groundbreaking or trailblazing. It's incremental, as we said, because authors, they take current solutions to different problems and they apply it on a smaller scale and in different combinations, which is definitely novel by itself. I mean, usually the solutions are developed. For example, peer-to-peer communication has been used in the past in different scenarios. They applied it to their solution, and the the group networking, the group helper groups are also a very interesting approach, even though it's been done in the past, and clustering and all of that. The peer-to-peer communication within the group and reassignment within the group was a very, very interesting and incremental approach that solved the problem. Of course, we had a very good experience reading this article. As we said, it's very informative, and we hope that we gave good feedback and gave the authors all the credit they deserve for doing this, putting the work into this, and we hope you enjoyed our presentation. Thank you very much.